Hi, this is Mr. Barron. I'm going to be showing you type 2 binary nomenclature, which picks up after type 1 nomenclature, where we're talking about how to name salts. Primarily where you just had to change the last part to "ide," and when you went from the name to the formula, had to pay attention and charge. Well, type 2 binary nomenclature takes it another step, and this other step only involves one additional rule. So it's only one rule beyond where we last were. So let's remember that for all binary nomenclature, it's going to be the same as type 1. All those rules about changing the N to "ide, and of course keeping polyatomic ion names the same, are all still in place. But there's a huge but, significant one. But some elements, particularly transition metals, can have variable charges. What this means is that if we look at the periodic table, these guys in the middle do not necessarily always have a consistent charge. It's different than the ones we were talking about, like the alkali metals. Every single one of those elements, always positive 1. Every single one of the alkaline earth metals, positive 2. All the halogens, all negative 1. Oxygen and sulfur, always negative 2. Nitrogen and phosphorus, always negative 3. So these rules are consistent for the far ends of our periodic table. However, in the middle, the charges can be different. Classic example of this is iron. Iron actually isn't always positive 2. When we first learned about the transition metals, I'm going to kind of block it out here. The transition metals we learned were always about 2 valence electrons usually, and they always typically had a positive 2 charge. But it turns out that iron is not always positive 2. Sometimes it can also be positive 3. Or let's take, for example, a different element. Let's look at, say, copper. Copper can actually be positive 1, or it can be positive 2. The only ones that are transition metals and are always the same charge are the ones that I'm going to be highlighting in red here. I'm going to put a box around them. And because they're really important, I'm going to put blue in my box as well so you can tell the difference here. So silver is always positive 1. Zinc is always positive 2. And aluminum is always positive 3. I like to think of this as the charge slide. These three always have the same charge. However, elements from here all the way, and including down here as well, I'm going to kind of highlight these guys as well, they can have what are called variable oxidation states. Oxidation states is the same as saying a charge. So they can have different charges. And it includes the elements that are outside the central transition metals. It can include lead, because lead can have either a positive 2 charge or it can have a positive 4 charge, depends. So what we're going to do is we're going to do some examples where we're dealing with elements that have different charges, and we're going to learn how to deal with them. So the example that I'm going to give you is, say we are dealing with a compound. We're going to go from formula to name. Say I have Fe2O3. Well, the rules for naming are exactly the same as type 1. So the first name is definitely iron, the second one is definitely oxygen, but I have to change it to oxide. But you may have noticed I left a huge space in between these two, and that's because I have additional work to do. See, iron can be either Fe2+, or it can be Fe3+. The only way to figure out whether this iron in particular in this compound is the 2+ or the 3+ is to infer it, meaning we have to figure it out based on the ratio that's here. Well, this is going to take some additional steps. So I'm going to rewrite the Fe2O3 down here, and I'm going to be labeling it with stuff I do know. Well, one thing I do know is that the oxygen doesn't have a variable charge. It's always the same. Oxygen is always, without a doubt, negative 2. So if oxygen is negative 2, always, and I have 3 of them, I know that that's a total of negative 6. So I know that for this compound to be neutral, these 2 irons have to add up to be a positive 6 charge, so that when you add positive 6 plus negative 6, you add those 2 together, you're going to end up with 0. So I know I have 2 irons, so you can infer that the charge is going to be positive 3. Now it's positive 3 for each iron. Remember, we want to think of these things as individual ions all packed together. So since I have 2 irons and 3 oxygens, this might be a better way for you to see it, is that we know each oxygen has to be negative 2. And if each oxygen has to be negative 2, the total is going to be, of course, negative 6. We know that the irons have to add up to be positive 6 to give me my neutral charge when I add them together. So these two have to have the same charge, so it would be positive 3 for each of them. So this is going to be iron that in this compound is positive 3. You're going to assume that you're not going to have like 1b iron positive 2 and 1b positive 3. No, assume they're going to be the same. So since my iron is positive 3, and I could figure that out from the oxygens in the formula that I have here, and you can do it looking at it in either method depending on how you think. How do we represent in the name that it's iron positive 3 and not iron positive 2? Well, what we do is we put parentheses right after our iron. That's why I left the space there. And what we do is we write a Roman numeral to represent the charge of the iron. I'm going to write Roman numeral 3 because it's actually positive 3. And this is the name that represents that formula. This is actually an easier system than what was used back in the day. In fact, they used to use completely different names. They wouldn't call it iron, they'd call it ferrous or ferric to represent which charge it is. So now we're going to look at a different problem. Let's look at one dealing with iron again, but this time when we're looking at iron, notice that it's going to be a different formula. It's FeO. Since it's FeO, we have to translate the name. Again, it's going to be iron, and then of course it's going to be oxide, just like the last one. But this time it's probably really easy to tell that since we only have one oxygen, and it's we know it has to be negative 2, the iron is going to be positive 2 to balance out the charge, because the charges of all of these ions in a compound always add up to be neutral, meaning there's no charge when you add all the numbers together. So this one's going to be positive 2, so I use a Roman numeral. And that is the difference between the two types of iron and the two different types of formulas that you get from these two different types of iron. So it's really, really, really critical that you remember which ones we have to pay attention to with these Roman numerals. So the rule that we need to remember is that you're going to use a Roman numeral for, and I actually want you to print out another copy of the periodic table, and it's for all of these guys right here. Not group 1, not group 2, because these are always consistent charges. It's all the transition metals plus these ones below the zigzag line here. These ones do not need Roman numerals, aluminum, zinc, and silver. It's only the elements that can have a variable charge, meaning the charge can be one thing or it can be the other. And then, so you want to possibly print it out and color code it kind of like I have, or the alternative is to draw a really cheap periodic table, which I'm not drawing precise at all. And it's basically this region in here. All of those guys need Roman numerals, except, of course, the ones on the slide, which we were talking about, which is aluminum, zinc, and silver. And you definitely have to memorize that. But it's conveniently within the boundaries of the transition metals plus the ones below here. And you know the slide, basically, that I taught you where aluminum's positive 3, zinc is positive 2, and silver's positive 1. The only way you can figure out what the Roman numeral is, this is the way to figure out if you need a Roman numeral. The way that you figure out what the Roman numeral is you figure it out based on the other ion that's bonding together. So I'm going to do another problem, and in this problem we'll show the same thing, where we're going to go from the formula to the name. So now I have CrCl3. Alright, I need to translate this. I'm going to start with rules from type 1, which is I write the first one, chromium, and I write the second one, chlorine, but I change it to chloride. Okay, now the first question. There's always two questions you should ask yourself. These are the cues that you need to pay attention to. Question number 1. Does it need a numeral, a Roman numeral. So I'm going to look. Let's find out where chromium is. Chromium is in the region where there are different charges, so it does need a Roman numeral. So I am going to have a Roman numeral squeezed in here between chromium and chloride. All right, number 2. Figure out charge for metal. And it's only metals that have the variable oxidation states or variable charges. Figure out charge for metal. And the way I figure it out is like I did before. I have 1 chromium and I have 3 chlorines. I can only figure out the charge of the chromium based on knowing the charge of the chlorines. Now, I actually should be calling them chlorides because they are ions. Here's chlorine. It will have a -1 charge because it has 7 valence electrons. So each of these are -1. If each of those are -1, my total is -3. And I know that whatever the charge of that single chromium has to add to the -3 to give me 0. So naturally it's +3. So the chromium is +3, so my Roman numeral is going to be Roman numeral 3. It actually takes quite a bit of practice to get comfortable with this, but once you've done quite a few, you start getting a lot better at it. Alright, let's do one more problem. This time we're going to be dealing with TiO2. Alright, follow type 1 naming. Let's write it out. Titanium, oxygen becomes oxide. Question number 1. Does it need a Roman numeral? Alright, let's look. Does it have a variable oxidation state? A variable charge? Now look, here's titanium. It's definitely in the region I need Roman numeral, so I do need one. So I'm going to put parentheses because I need my Roman numeral. Next question. What's the charge of it? Well, the only way I can figure out the charge is from knowing the charge of this. It's the metal that has the unknown charge. So let's write out how many I have. Ti, and I have 2 oxygens. Alright. Oxygen, I know, has to have a -2 charge. It has to. Since it has a -2 charge and there's 2 oxygens, these 2 negative charges add up to be -4. So what adds up to -4 to give you 0? Well, +4. So titanium, in this case, has a +4 charge. So my Roman numeral is Roman numeral 4. Now, if you don't remember your Roman numerals, you only have to go up to about 7 in this class. So Roman numerals go 1, 2, 3, 4, 5, 6, 7. That's as high as you're going to go. Alright, let's do another problem. This one, we're going to go from formula to name. So AgNO3. It's a 3 there. Alright, question number 1. Well, actually, let's do the type 1 naming because you always have to do that no matter what. So it's silver, and it's nitrate. Doesn't need a Roman numeral. Here's silver. Up. It's in my slide. I know it always has a +1 charge. Doesn't need a Roman numeral. I'm done. That's it. Make sure you knew that the nitrate, of course, was a polyatomic ion. Alright, let's do another one. This time, let's see here. Let's do Pb CO3 in parentheses 2. So let's follow the type 1 naming. It's lead. CO3 I know is carbonate. Question number 1. Does lead need a Roman numeral? I look, lead's down here. I know it has this variable charge. It can either be +2 or it can be +4. So I know it needs a Roman numeral. So I'm going to put my parentheses ready for the Roman numeral. Now let's write out our little chart here to see what the charge might be. I can only figure out the charge of the lead from the carbonates. There are 2 carbonates, so I'm writing them out separate. Make my little T chart. And I know, I've memorized, that carbonate has a -2 charge. You should have memorized, or at least had a handout that you can use to remember what the charge of all the polyatomic ions are. So there are 2 carbonates, so that's a total of -4. So I know that whatever the lead is, it has to add up to be the same charge as my -4. So it has to be +4, which means Roman numeral is 4. And that's the answer. Now, we've been practicing going from the name, or from the formula to the name. Now we're going to go the other direction. Believe it or not, the other direction is actually a lot easier. So what we're going to do is we're going to look at a couple of different names and translate them into the formula. So let's take a look at the name cobalt 2. Let's make it sulfide. Alright, cobalt is CO, sulfide is S. So what's the charge of the cobalt? Believe it or not, it's already given to me. Remember, the Roman numeral comes after the metal, which gives you your charge. So cobalt is positive 2. Sulfide, I gotta look it up, it's in the negative 2. It's always negative 2. S2 minus. The charges are the same, so I don't need to do my crisscross rule. I can just write it as COS. Don't forget, just like type 1 naming, when you're going from the name to the formula, you do actually have to pay attention to charge. When we're dealing with type 2, when we're dealing with Roman numerals, you always have to pay attention to charge. Let's do a couple more. Let's take a look at nickel 4 nitrate. Well, I know nickel is Ni. I already know its charge. It's given to me because of the Roman numeral. It's positive 4. Nitrate I know is NO3 minus. Well, they're not the same charge, so I do have to do my crisscross rule. So I'm going to take my pen and cross down the 1 that goes down here, but I don't write 1, so I'm just going to leave it Ni. And then the 4 comes down here. So Ni, NO3, 4. And hopefully you remember, we don't want it to look like there are 34 oxygens. Remember, it's 4 nitrates that are here. And that's the formula for nickel 4 nitrate. Definitely practice this on your own. The only way you're going to get good with naming in chemistry with chemicals is to practice a whole lot. The more you do, the better off you'll be. Good luck.